All right, let's jump straight into this explainer and look at a seriously fascinating thermodynamic mystery happening right inside our homes. I mean, have you ever stopped to wonder what's actually going on inside your air conditioner to make your room feel so amazing? Well, today we're unpacking the secret temperatures and the hidden physical reality that keeps you cool. We're going to look at some pretty surprising numbers that govern how these machines actually work behind the scenes.
You know that feeling when you catch that perfectly cool breeze right from the vent? Well, what's really interesting here is the hidden gap between what you're feeling and what the machine is actually doing to make it happen. There is this massive difference between the air hitting your face and the temperature of the internal components actually making that air cold. So let's break down the exact numbers. When your AC is running perfectly, the discharge air, that supply air cooling down your living room, is usually sitting right around 16 degrees Celsius, or about 61 degrees Fahrenheit. That is a perfectly crisp, super comfortable temperature. But here's where it gets wild. If you were to look deep inside the unit itself, the surface temperature of the evaporator coil is sitting at a remarkably chilly 4 to 10 degrees Celsius, which is 39 to 50 degrees Fahrenheit. I mean, it is literally nearly freezing in there. So, doing the math, the crucial point is that we've got a missing 6 to 12 degrees Celsius or an 11 to 22 degree Fahrenheit gap. The internal coil is always significantly colder than the air leaving those vents. In HVAC engineering, this missing temperature is known as the thermal transfer differential. But where does the heat actually go? Like, why doesn't the air just match the coil temperature? So here is our quick game plan for today. We'll start with the temperature gap mystery, then look at the physics of cooling, followed by the variables controlling coil temperature. After that, we'll get into diagnosing your AC system, and finally wrap up with the freezing hazard. All right, part one, the temperature gap mystery. This is literally thermodynamics in action. Our first key concept is something called the approach temperature. Now, in HVAC engineering, the approach is the difference between the fluid inside the tube, which is your refrigerant, and the fluid flowing over the tube, which is your room air. The fundamental issue here is that air is honestly a terrible conductor of heat. Because of this, as that warm room air passes through the coil, it simply cannot instantly drop to the exact temperature of those freezing cold metal fins. It needs time and it needs contact. And that brings us to the contact factor. Imagine the air rushing through your air handler like a massive, chaotic crowd trying to squeeze down a narrow hallway. Not every single air molecule is going to bump into the walls, or in this case, those freezing metal coil fins. The air that bypasses direct contact just doesn't get as cold. It simply mixes with the air that did touch the coil, resulting in a final, blended discharge temperature that is quite a bit warmer than the coil itself. And that right there is exactly why you get a 16-degree vent breeze from a 6-degree coil. Moving on to part two, the physics of cooling and the variables that are constantly shifting these temperatures. So, your first major variable is airflow velocity, basically your fan speed. If you crank up that fan speed, you are moving a whole lot more warm room air over the coil every single minute. That high thermal load actually keeps the coil slightly warmer, typically closer to 8 to 10 degrees Celsius. On the flip side, if you use a low fan speed, the air moves much slower. This allows the incredibly cold refrigerant to strip away way more heat from fewer air molecules, dropping the coil's temperature down closer to a really chilly 4 to 6 degrees Celsius. The second major variable we have to look at is the latent heat load, which is your humidity. When humidity is high, the coil works incredibly hard to condense that moisture out of the air. This phase change actually releases latent heat directly onto the coil, physically warming the coil's surface. But if you have low humidity, the coil is mostly performing sensible cooling, just lowering the air temperature without condensing much water, which allows that coil to run significantly colder. Finally, the third big variable is the entering air temperature, or the return air coming back from your room. Picture walking into a sweltering 30-degree room. That heavy initial heat load is going to absolutely force the coil temperature to the higher end of the spectrum. It's going to stay warmer until the room itself finally starts to cool down. All right, part three, diagnosing your AC system. Let's see how professionals actually read your system's health. Monitoring the relationship between all these temperatures is basically the ultimate diagnostic tool. In a perfect, ideal state, your room's return air pulls in at around 24 to 26 degrees Celsius. The discharge air blowing out is a crisp 16 degrees. That means you've got a perfectly healthy 8 to 10 degree temperature drop. And underneath it all, the internal coil is sitting safely at 6 degrees Celsius.
If you see these numbers, your status is absolutely perfect. The system is efficiently absorbing heat and removing humidity with zero risk of freezing. Which brings us to part 4, the freezing hazard. This is what happens when those coils drop below 0 degrees Celsius. This step-by-step chain reaction shows the freezing hazard, and it's a huge deal. If your system is trying to maintain that 16-degree discharge, but the internal coil drops below freezing, you have a severe problem. Step 1 usually starts with restricted airflow. We're talking dirty air filters, blocked vents, or a failing blower motor preventing warm air from hitting the coil. Or it could be a low refrigerant charge, where a tiny leak causes the remaining refrigerant to overexpand. Step 2, the coil instantly plummets below 0 degrees Celsius. Step 3, this causes rapid, immediate ice buildup on the coil. And since ice acts as an insulator, we hit step 4, airflow blocks completely, and the discharge temperature you feel rises right back up to room temperature. The machine is essentially suffocating itself.
Finally, part 5, a technical summary. This is your system cheat sheet.
Pulling all of this together, you've got your discharge air at 16 degrees handling the room, and your typical coil temperature resting roughly 6 to 10 degrees below that at its active boiling point. That delta between the air and the coil is your actual efficiency gap. And the very moment you cross that 0-degree freezing threshold, you are completely in the danger zone for coil icing. Now that you know the invisible physics of your AC, take a look around your own environment. Are you experiencing weak airflow or maybe some mysterious leaking right now? But on a much grander scale, think about this. If this highly delicate thermal dance is what governs a simple living room, just imagine the extreme thermodynamic balancing act happening right now inside the massive data centers powering our entire digital world. Honestly, how close to the freezing threshold do you think they're running? It's pretty wild to think about. Until next time, keep observing those hidden systems all around you.